Yeah. So, I'll get started. So today I'll talk about my recent work done at NVIDIA with Marco, and then the title of today's talk is Object Pose Estimation with Statistical Guarantees. And there are really just two techniques that we are using here. The first one is called conformal key point detection, which I'll briefly describe. And then the second one is geometric uncertainty propagation. And that one is really the one that I want to dive in a little bit today. And I think it will be interesting for today's audience, which I think the technique we're using is actually something from control theory. So let's just dive straight in. Usually I would have a kind of motivation slide, but today I want to spend as much time as I can on the technical details. So I just dive straight into the problem. So the problem is object pose estimation in computer vision. So in this problem, we're interested in estimating the 3D rotation and translation for example, in a vehicle from a 2D image. And then in this task, a typical perception pipeline works as follows. So in the first stage, the perception pipeline can use a neural network, usually a pre-trained neural network, to detect semantic key points on this 2D image. And also these detected 2D semantic key points are going to be in correspondence with 3D key points. So for example, here I'm showing some key points of the mirrors, of the doors, and the other things in the vehicle. And then usually, and this step is typically called the feature matching front end of this perception pipeline. And usually in practice, because the pre-trained neural network is not perfect, and maybe the test data is not really in distribution, so there may be a lot of wrong detections outputted by the front end, and these are the so-called outliers. And then the second stage of this pipeline really seeks to estimate the 3D rotation and translation of this cat model using this set of correspondences that are corrupted by outliers. And this step is typically called the model estimation backend of this perception pipeline. And one of the most well-known algorithms for solving this estimation problem is called RANSAC, and which stands for random sampling consensus. And as this name suggests, RANSAC works by randomly sampling a subset of this given set of correspondences until some consensus is reached and some satisfactory solution is found. And the result of RANSAC is actually pretty good in most of the times. So you'll get a pretty accurate model estimation like the one that's already shown here. But in difficult cases, RANSAC will fail and give you a wrong estimation like this one. So I'm really interested in safety critical applications. So why, what can go wrong in this object pose estimation pipeline? So I argue that there are really three challenges in making this perception pipeline trustworthy or safe. So the first challenge is that these algorithms like RANSAC, these are heuristic methods that are trying to solve some NP-hard a numerical optimization problem. And therefore, these algorithms can really get stuck in local minima without giving you any notice. So that's the first challenge of this perception pipeline. And the second challenge is that even if we assume that RANSAC and these heuristic methods can actually give you a global optimal solution, then the pipeline is actually still not trustworthy. And the reason is because these algorithms, their input depend on the key points. And these key points are outputted by these black box neural network models. So if these key points are arbitrarily wrong, then even if you solve these optimization problems to global optimality, then the optimal solution may not even be the desired ground truth solution that we want. So that's the second challenge. And the last challenge, which I think is a little bit unknown in the field, is that even if your key points are correct, let's say your key points have some bounded noise, and let's say your RANSAC algorithm also succeeds, but then really the thing that we need is that we want the solution to be close to our ground truth pose, to our ground truth solution. And actually in the field, there is no provably correct uncertainty estimation of these optimal solutions. So really, ideally when we have a state estimation result like this 3D rotation and translation, then we need some bounded uncertainty from our estimated solution to the ground truth. And how do we solve these three challenges? For people who may know me a little bit, in my PhD, I've mainly focused on the first challenge, which is to make these heuristic algorithms with certifiable guarantees. And then the solution here is that we use these convex relaxations to solve these to relax these NP-hard optimization problems to convex problems. And then from there we can get a solution in polynomial time, and also we get a certificate of global optimality. But actually, that line of research hasn't addressed the second and third challenges, which is how do you ensure the key points are good, and how do you ensure that the solution we obtain has some error bounds from the ground truth. And this talk, we aim to give an answer to these two challenges. So this is an overview of the solution that we propose, and we call it object post estimation with statistical guarantees. So the thing is that we really bring two fundamental changes to this object post estimation pipeline. And the first fundamental change is that instead of using a black box neural network model, we use something that is called inductive conformal prediction. And then we basically wrap this black box model in this statistical framework called inductive conformal prediction. And then after you wrap this black box model into this statistical machinery, then this front end becomes something we call conformal key point detection part. And then a result of this conformal key point detection is not these simple point-to-point correspondences, but actually a prediction set for each of the key point. So for example, if we only look at the headlight of this vehicle, then after conformal prediction, it will give you something like a circle, and this circle this circle will something like a circle on this 2D image, and I'll be able to guarantee you that this circle contains the ground truth headlight with 90% confidence or 95% confidence. So the confidence is actually specified by the user. So if you want me to be more confident, then I'm going to give you a circle that is larger. But if you can tolerate unconfident predictions, then I will give you probably a smaller circle to tell you that the ground truth key point is actually within the circle. But
just a quick question. So when you say it's a circle, is it always a circle exactly, or is it some sort of shape that contains this key point?
Yeah. So I will tell you a little bit more about the conformal framework later. But right now we have so the circle is just an instance of some prediction set that the front end can output. So it is by design. So you can design the shape to be any shape that you want. So we've tried circles and ellipsoids. But I think it is also possible to design this shape to be, for example, a box. So, but that will require changing some design components in the conformal key point detection part. But the essential story here is that these circles or any shapes that you design, this this statistical machinery will provide you statistical guarantees of these prediction sets actually containing the ground truth key points. So we'll have one key point, we'll have one circle or one such shape for each key point, and eventually we're gonna have for if this vehicle has k or 10 key points, then we'll have these 10 different circles. Some of them may be larger, some of them may be smaller. So that's the first thing that we bring into this we change in this pipeline. And the second thing that we change is that instead of solving some mathematical optimization problem whose cost function is usually handcrafted, right? So no matter in computer vision or control, there is handcrafting the cost function is always some engineering effort that we need to do. And then in this new work, we kind of propose that we're not going to do we're not going to handcraft our own cost function, but what we will do is to only propagate the uncertainty in the 2D key points. So these kind of different circles or different shapes, they give us some kind of bounded noise along the key points, along the ground truth key points. And we will just propagate these bounds or propagate these uncertainty from these key points to the 3D rotation and translations. And the result of this is something that we call a post uncertainty set, which in short we call it a PURSE. And then this post uncertainty set is going to be some non-convex set, but we will have kind of scalable ways to kind of characterize this kind of post uncertainty sets. And specifically, for one of these examples, we actually were able to plot these uncertainty sets of the rotation and translation. And you can see that if you plot the rotation uncertainty set in terms of the Euler angles, it's gonna look like some 3D shape that's probably a potato in this picture. And then if you look at the translation, it is going to be something like this rod that is, or like maybe even some satellite. This one has a larger uncertainty in the z direction, but have smaller uncertainty in the x and y direction. So that's what we'll do for the geometric uncertainty propagation. But then because these uncertainties are being directly propagated, we will be able to maintain the probabilistic guarantee of the key points, which means that we will be able to guarantee that with 90% confidence or 95% confidence, the ground truth poles will actually lie within this purse. So that's the the high level overview of the machinery that we redesigned, for how we have redesigned this perception pipeline. So in today's talk, I will just I told you that I want to kind of briefly talk about the conformal key point detection, just so that we are a little bit familiar with the machinery and the notation for this problem. And then, of course, the majority of the work, of the talk today will be, I will talk about the geometric uncertainty propagation. So let's, see how conformal key point detection works. So the setup here is that, we have a 2D image. RGB image, we're in X in H and with dimension H, W, and 3, where 3 is the number of channels, RGB values. And then our goal is really to predict a set of K key points. So let's say the vehicle here has K semantic key points, and I've drawn kind of 4 key points here. The K's key point, YK, will be something, the ground truth will be something here. These are labeled key points. You can usually the popular computer vision data sets will provide you with these ground truth annotations. And then, in practice, one can pre-train any, fancy neural network. Here we just denote this as a black box function F. This F function will take in this image X, and what this F function is. Go ahead. Was there a question? Okay, I guess there wasn't. So this black box function F, it's going to take in this 2D image X, and it's going to give us a set of heat maps. So it's specifically, the kth heat map of this neural network is going to tell us the probabilistic, the expected probabilistic distribution of the k's key point YK lying on each pixel of this image. So for example, here I'm showing just an example heat map. So this, the yellow part of this heat map says that there is larger probability of the ground truth being there, but then the blue areas say that there's very low probability of the semantic key point YK lying on those pixels. And then usually after you get some sort of heat maps like this, in practice, what you usually do is to take the pixel that gives you the highest probabilistic value, which we call a Q star, and you will use this Q star as your estimated location of the semantic key points. Let me see. There's a chat. There's a question in the chat. Not clear why this.
No, it's okay. No,
okay.
He just was apologizing for unmuting accidentally.
Oh, okay. Actually, okay. Yeah, because I actually cannot find my mouse. So okay, let's keep going. So this Q star will be some estimated location of the ground truth key point, right? And the problematic part of these black box models, as I said before, is that these Q star can be arbitrarily far away from the ground truth key point YK. So when the distance between Q star and YK is large enough, we sometimes call it an outlier. So that's the usual practice in detecting semantic key points. But then the machinery that we will use here is called conformalization, and the conformalization step comes from the statistical machinery called conformal prediction or inductive conformal prediction. So I will tell you what you will need to use this machinery and what it will output for you. So you will need 3 things to use this conformalization step. So the first thing is something called a calibration set. So this calibration set is something like the validation data set in the machinery, usual machinery pipeline. So the calibration set is basically a set of X and Y's that you have not trained your function F on. So this calibration set usually can be a set of, for example, 200 samples or 500 samples. You don't need the calibration set to be as large as your training data set. Usually 500 or 1,000 or 200. These are good sizes. And then the second thing is that you will need something called a non-conformity function. So this non-conformity function can be an arbitrary function, but usually that's the place where we embed our design choices. We embed our inductive biases to this non-conformity function. And using different non-conformity function will give you different outputs. Basically different shapes of the prediction sets. And the third thing, which comes from the user. So the user will have to specify something called an epsilon. So this epsilon is basically an expected error rate. So by setting this epsilon to be, for example, 10%, then the user asks this conformalization step to give me outputs that can fail with the probability around 10%, but not too higher than 10%. So basically, this is 1 minus epsilon will be the confidence, and then the output of this conformalization step will be some prediction set. So for example, here I give you 4 prediction sets, 1 for each ground truth key point, and then the prediction set by using our non-conformity function will have the form of this. So the prediction set will be we will call it f of epsilon. So basically, this capital F here means that it's going to give you a set of predictions instead of just a single prediction. And epsilon here is a user specified error rate. So this f epsilon is going to take a new image, which we call xl plus 1, and then it's going to give you a bunch of a union of basically a product of 2D circles, where each of this ball or circle has a center at Q star and it has a radius that we call RK. So this RK has some formulation which is actually pretty simple, but I ignore it here to just keep the formulation simple. So basically, it's going to give you a bunch of these yellow balls that will guarantee that the probability of the ground truth key points lie within my f epsilon will be larger than 1 minus epsilon. And basically, this is a probabilistic guarantee that we will be able to make on average. So what I mean by on average here is that this probability, of course, is over the randomness of the calibration sets. So one can imagine that if you choose different calibration sets, then your empirical coverage, which is if you use some calibration set and use some non-conformity function, and you get these sort of prediction sets, and you evaluate it on some test data set, you'll get some empirical coverage, right? So that empirical coverage will actually vary between different calibration sets. But then there's a theory saying that the empirical coverage will not deviate too far away from 1 minus epsilon. And in fact, in the experimental results I showed you later, they're actually going to be pretty close to 1 minus epsilon. So for example, if your expected confidence is 90%, then the empirical coverage will be, for example, 88%, 92%, but not 70%, not too far away from the expected 90%. And you will be able to quantify how large that deviation will be by using some distribution of the empirical coverage. So that's the theoretical probabilistic guarantee that we'll be able to make from this conformal or key point detection. So hopefully now you are a little bit familiar with the notation of this problem setup. So now we go to the second part, which is really I think the thing that I think is more interesting for today's audience is how do you propagate this type of uncertainty to the poses. So before we kind of discuss how we propagate this type of uncertainty, let's perhaps see what's the kind of canonical way that people use to estimate poses from this prediction sets, right? So let's see, now you are given these type of prediction sets with these ball shapes. Usually what people do is to formulate some uncertainty aware perspective endpoints problem. So this will be some optimization problem that of the following form. So here RMT is the unknown camera pose or unknown rotation translation that you are trying to estimate. And then pi here is the camera projection, which is some a rational function of the input here, that is r times yk plus t. Here yk is a ground truth 3D key point that from the labeled 3D CAD models. So r times yk plus t will bring the 3D key point to the camera frame, and then you project the 3D key point to 2D, and then you evaluate its its distance from the reprojected key point to the predicted key points that we call QK, which is actually the center of these balls. And of course, you want to do some nonlinear least squares, with some weight that is proportional or inversely proportional to the size of the prediction sets, right? So if the prediction sets are larger, then it means that I want to place a little weight on this single key point. But if the prediction sets are very small, that means I'm very confident about that prediction. So therefore, I want to put larger weight into this residual or this semantic key point. So that's the canonical way that people use to solve this type of problems. And actually, there's a bunch of literature on actually how to solve these optimization problems. But I argue that this may not be the correct way to solve this type of problems. So the first issue is that this problem itself is actually very difficult to compute. So in order to solve this optimization problem, because the pi here is a rational function, so you actually need quite a lot of machinery to solve this problem. And from my understanding, the best algorithm out there today is based on, for example, branch and bound. That is worst case exponential time to solve this problem to global optimality. And otherwise, you'll have to resort to local optimization or local nonlinear least squares to solve this type of problem, which have the issue of getting stuck in local minimum. And then really, that's the first issue. And the second and third issue, I think, is more important, is that when you solve this problem, you get a single optimization problem, R star and T star. But what can we say about this optimal solution, right? Can we say anything about the uncertainty of these R star and T star? More precisely, can we give some type of bound from the R star and T star to my ground truth? So that's really something that I don't think anyone has ever addressed in the computer vision literature. And then to resolve this kind of three difficulties, we turn to control theory for help. This is actually in hindsight. I wrote this paper before, and then I was discussing this idea with someone else, and then he pointed out to me that actually there is this very classical result in control theory that is actually very analogous to the approach that you've been using. And then I took a look at this paper, which actually is quite similar to the machinery that have been used. So this classical result in control theory is called set membership estimation, or unknown but bounded noise estimation. So really the idea here is that when we are given a set of measurements, then we form a set on the models that are compatible with my measurements. So specifically, let's look at in our case, we have this we have each of this key point defining us an inequality constraint on the ground truth key point yk, right? So we can rewrite this original equation into this canonical form, which is a 2D ellipsoid or 2D ball. This lambda k here will be some a kernel or 2x2 matrix that describes the shape of this prediction set. So basically, the canonical form of this equation says that my ground truth yk, the distance from yk to the center qk star, will be bounded away by this ellipsoid or ball. And then we will actually rewrite this equation into our poses, as in terms of our poses. And the way you rewrite it is actually by rewriting the yk, but as the 2D projection of the optimal of the ground truth rotation times the ground truth 3D key point plus the t, right? So that's the you've also seen this this equation in the optimization problem that we've just shown. But instead of optimizing it, here we're just writing it down, and then we're gonna rewrite this inequality constraint now in terms of my model S. So the S here is the concatenation of the vectorization of R and the 3D translation, which will be a vector of 12 numbers, right? So, and then by using this, you will be able to get okay, and I finally get my mouse. Okay, let me move this zoom away. Okay, so we've talked about okay, I think we're here. So we can rewrite this inequality constraint now as a quadratic constraint on my model S. And then you have this AK, this is a 12 by 12 symmetric matrix that is not necessarily a positive semi-definite or positive definite. These AK matrices will depend on your data. And then the BK transpose times SK here is just a linear inequality constraint that enforces the 3D key point to be in front of the camera. So that's basically what we are saying here is that one single key point will give us one quadratic inequality and one linear inequality. And then if we concatenate all these k different key points, we will be able to get something like what we call a purse here. That is a subset of SE3 that satisfies these k quadratic inequalities and k linear inequalities. So that's what we call a post uncertainty set. So of course, because these kind of inequalities are direct reformulations, we have not done any relaxation here. So we will be able to maintain the 1 minus epsilon probabilistic guarantee. So basically, we will be able to guarantee that the ground truth pose lies within my purse with 1 minus epsilon confidence. Okay, so that's what I've showed you this picture of this purse. But then this purse, one needs to be cautious is that this purse is actually a non-convex set. I told you that this.
Before you continue. Sorry, quick question. So you've got 1 minus epsilon probability on each of the k's. How do you say it's still with 1 minus epsilon probability on the entire set for all k?
No, so actually by a redesign, by a redesign of the non-conformity function, you can guarantee that this, this k balls, they contain the k key points together jointly with 1 minus epsilon probability.
Okay, I see. Okay.
So it's not on the single key point. Of course, you can do it on single key point, which is, the original idea was published. This conformal key point detection idea. I had a kind of numerous workshop, and in that kind of very preliminary version, we are doing it on a single key point. But then, we immediately realize that, if you are reasoning about a single key point, then when you reason about the, k different key points, you lose the probabilistic guarantee, right? So that's why we kind of redesigned the non-conformity function a little bit. It actually is very simple. And then by using that new non-conformity function, we will be able to maintain the 1 minus epsilon probability on all the key points.
Okay.
Okay, so so that's by the way, that's a very good clarification. So this purse will be a subset of SE3, with these non-convex constraints. So therefore, it's definitely some nasty non-convex set. So how do we characterize this post uncertainty set, right? Or how do we use it for our downstream tasks? So the first thing we might want to do is to check membership, right? If you give me something as in SE3, if you give me a 3D rotation and translation, I want to check if that pose is actually in my purse. That of course is very easy to do. You can just evaluate these quadratic inequalities and linear inequalities. And that you should be able to do it very quickly. And then the second thing that we're interested in is, there's this nasty non-convex set of poses. How can I generate samples, right? How can I, look at samples of this non-convex set? So that actually is actually a very tough problem in general. So if I give you a non-convex set and I ask you to generate, samples from this non-convex set, it's actually a non-trivial problem. But for this problem, actually, we can use sort of the inverse problem to actually solve it. So how do we generate samples? We design sort of an algorithm that we call RANSAC, which is random sample averaging. Instead of RANSAC, we're using RANSAC, and the idea here is very similar to RANSAC. So the idea here is that although it's very difficult to sample directly in my purse, but it's actually very easy to sample within my 2D semantic key point prediction sets, right? So I have a bunch of these yellow balls here. I can draw samples in these balls, very easily, right? So if it's an ellipsoid, I can also draw samples in those balls, in those ellipsoids, very easily. So what I do is I randomly choose 3 prediction sets. So these will be 3 balls or three ellipses, and then I'm gonna generate 3 random samples, 3 random 2D key points. I call them y hat of ki inside of these prediction sets. And then I've solved this P3P problem. So in computer vision, there's this classical result saying that you only need 3 key points in order to get you an absolute camera pose. So basically, by solving by having the three candidate key points, I can get a candidate rotation translation. And then, of course, you will, the candidate rotation translation will make sure that the reprojected key points also lie in the balls corresponding to those 3 choices that you've made. But it may not project the 4th key point on the 4th ball. So then you have to check, if this candidate rotation translation is actually in my purse. So if it's in my purse, then I get 1 sample. But if it's not in my purse, I just resample. So this is very similar to ransack, right? So in ransack at each iteration, it also does this random sampling and do this P3P problem. But in here we are only interested in doing sampling inside the purse. And then using these samples, we can do something called an average pose, right? So let's say I sample 1,000 times, I get, for example, 200 samples in this purse. Then you will be able to generate some average sample from this 100 samples, and that's what we call an average pose. So the average pose corresponds, and that's why this algorithm is called random sampling averaging. But then the average pose will be something kind of our estimate of the ground truth pose. But again, recall that the fundamental goal here is to bound, to get some type of arrow bound from any pose estimation to my ground truth, right? So the last thing that we're interested in is, can we actually derive some arrow bound from my average pose to the ground truth pose? So that's something.
Quick question: do you know that this purse set is connected?
No, we don't know. It's it's non-convex. We don't have any analysis about this non-convex set being connected or disconnected. We don't even know if it's non-empty or not. Sometimes it's actually non-empty. But you will be able to when it's non-empty, the algorithm will give you some. My conjecture is the algorithm will give you some signal. I'll show you in the numerical results.
Okay.
So basically, now we are interested in bounding the distance from my the average pose, or actually any pose that you've estimated, right? So but basically our goal is to solve this optimization problem, right? So my goal here is I have this purse which is defined by a bunch of inequality constraints or polynomial constraints, and I have my average pose here. My goal is to find the maximum distance from my average pose to my purse. So here I'm writing the cost function as an average of the rotational distance and the translation distance. But in practice, we evaluate it separately. So in practice, we only set lambda to be either 0 or 1. So basically, we are interested in the maximum rotational distance or the maximum translation distance. So and then my constraint here is that I want my RMT to lie in my purse, right? So this maximum distance from the average pose to my purse will be intuitively an upper bound on the arrow between my average pose and my ground truth, right? Because your ground truth lies within my purse, and I'm giving you the maximum distance from the average pose to my purse. So of course that is an upper bound. Of course, I should be more explicit that is an upper bound with 1 minus epsilon probabilistic guarantee, right? So because if the key points fail, then you still have a small probability that the ground truth may not lie within the purse. But in general, if you believe with 90% confidence that your ground truth lies within this purse, then you should also believe that this arrow bound is correct with 90% confidence, right? So that's how we compute the arrow bound. So this optimization problem now is easy to formulate, but it's actually also difficult to solve because it's still a non-convex problem, because you're maximizing over a non-convex constraint, and your objective value is also a non-convex. So in here, we just use a semi-definite relaxation, so that's, the kind of the convex relaxation story comes back into this problem. But then the nice thing about this problem is that this problem is actually much smaller and much easier to solve than the outlier robust, thing that I've done in my PhD. So this, we actually use we just use vanilla semi-definite relaxation to solve this problem. And we found that this the relaxation almost always gives you the global optimizer of this problem at order 2. And what's even nicer is that you actually let's say even if your relaxation is not exact, so then what you're getting is an overestimation or an upper bound of the optimal value of this optimization problem. So basically that upper bound, because it's upper bound of the optimal value of this optimization problem, which in turn is an upper bound of my error. So that even if the relaxation is not tight, the value you get is still an upper bound on the error bound, right? So on the ground truth distance, on the distance between the ground truth pose and my average pose. So that's a nicer thing here is actually you don't even need to solve this problem to global optimality, but in practice we just found it not so difficult to solve it to global optimality, and you can solve this problem in my machine. It can solve it in probably 5 to 10 seconds. But of course we have we're interested in making this even faster. But now this is already, I think it's already with kind of reasonable runtime, 5 to 10 seconds. So that's how we derive the error bound. This is this I believe is the first computable error bound in computer vision. People have done some theoretical analysis. The kind of first thing here is that there are not so many error bounds in computer vision, and then even if these error bounds exist, sometimes they're not computable because they have to rely on some uncheckable assumption. But this is the first time that you can actually compute the error bounds. And I'm really going to compute these bounds and show you some plots in the experiments. So that's the kind of high level overview of using this unknown but bounded noise estimation framework in control theory to a perception problem. But of course, the tailor that you have to make here is to design sort of the ransack algorithm and to design this kind of semi-infinite relaxation to solve the error bounds. So let me now describe how I do the experiments. Sorry, I already run quite over time, but I want to show you some results. So the experiments here is that we do it on this line mode occlusion data set. So this data set is a set of more than 1,000 tabletop images like this one. You have a table and you have different objects like the yellow duck here in this table. And then what you first do is to generate some bounding boxes. You're gonna crop these bounding boxes out of the original image so that you get these object-centric views of each of these different objects. And then you apply this black box neural network, which gives you keypoint predictions. And specifically, we're using the one that was designed by someone from UPenn. And then we can generate these key points, right? So you'll get the key point heat maps. Of course, these key point heat maps will be arbitrarily wrong. So that's why we apply these conformal machinery. We're going to generate a bunch of balls, yellow balls that with 1 minus epsilon confidence will actually contain my ground truth key points. And then you will do the geometric uncertainty propagation and evaluate our error bounds. So the calibration set size here, it has 200 images, and then the test set is 1,000 is more than 1,000 images. And when we evaluate two cases, where the first case is the user wants to be super confident, which is 90% confident, and then the second case is the user can tolerate a little bit uncertainty or failures in my key points. So in that case, we want to be 60% confident. So let's first look at how these prediction sets will look like, right? So these prediction sets, I gave you some qualitative examples of the prediction sets here. So this corresponds to the case of 90% confident. You'll see that if you want to be more confident, then you have to design the balls to be the kind of the conformal machinery will give you balls that are relatively larger than necessary, right? So each of this column shows you the ball for a single key point, and then the last column gives you kind of an overlap of all these different balls together on the object here. But if you can tolerate a little bit kind of failures in the predictions, then you see that these balls shrink significantly in terms of their size, right? So now you will be able to get pretty tight kind of prediction sets. These are here I'm showing balls and ellipsoids and they actually contain the ground truth key points. So the ground truth key point is shown as the squares inside those balls, and then the heat map, the heat map is also overlaid on this 2D image, and you can see that sometimes the heat map is actually pretty far away from the ground truth, but the ball can actually contain the ground truth with that specified probability probabilistic guarantee. So now, the second thing, as looking at these qualitative examples, we're interested in, is this, conformal prediction machinery valid, right? Is it actually the case that my purse actually does contain your ground truth pulse? So here we evaluate, this the empirical coverage. So in the epsilon equal to 10% case, we are shooting at 90% confidence, right? So if you look at the empirical coverage, you do see that. So here I'm plotting the empirical coverage for all 8 different objects. So we are doing this, so of course, because you have 8 different objects, you have to apply conformal prediction to each of these objects separately. And you'll see kind of this histogram of empirical coverage, and you see that they do fluctuate a little bit around 90%, but they're not going to be too far away from this 90%. And in fact, in most cases, it's actually above 90%. So if you actually ask for 60% confidence, then you also see that these kind of empirical coverage will be adjusted as required by your expected 60% confidence. So that's so basically the first thing we do is we kind of evaluate if the theory is actually valid. So now that the theory is valid, we're actually clear that these prediction sets or these purses, they do contain my ground truth pulse with that marginal probabilistic guarantee. Then the last thing that we do care about is now I'm computing my arrow bounds. Are my bounds actually valid bounds for the ground for the ground truth, right? So here I'm showing this interesting plot, which I think is actually very insightful. Is that here we are plotting rotation arrows in both the x and y axis. So the x-axis is the arrow bound that we've computed from solving that optimization problem, and then the y-axis is the arrow between the ground truth and my average pulse, right? So I'm computing the rotation arrow between my average pulse and the ground truth. And I'm also computing my arrow bound between my average pulse and my pulse set. So I told you that the pulse to pulse distance should be an upper bound for the ground truth arrow, right? So that's why I'm plotting this y equal to x diagonal line. So everything that lies below this y equal to x line means that my upper bound is indeed a valid upper bound. But everything that crosses this line means that it's not valid, or it's not correct. So here I'm showing these scatter plots in 2 colors. So the blue colors means that those are the cases where my pulse actually contains the ground truth pulse. And the first message you see here is that when the pulse contains my ground truth pulse, these arrow bounds, they never cross the y equals to x line, which means that my arrow bounds are indeed always correct if my pulse contains my ground truth pulse, right? So that's the first thing that you should verify, because that's what the theory has told you, but it's kind of nicer to see it in real experiments. But then the second thing we care about is, are these how tight are these bounds, right? So if you look at this cluster, which is the majority of the cluster, these actually give you reasonable bounds. I'm not saying that they're super tight, but they are actually reasonable, right? So if you look at some of these points, they have kind of the real arrow is kind of 10 degrees, but I'm giving you a bound that is 20 degrees, or sometimes more conservative, like 50 degrees. So those are reasonable bounds. But then here, these are the conservative bounds. So these are conservative bounds saying that look at these bounds, you see that the bounds you get here is 180 degree, which is the maximum possible bound, right? So this means I'm giving you very loose bounds. I think this corresponds to the case where the pulse is not even bounded, or is not even closed or something. So that's why they give you type of this kind of very conservative bounds. But then when you also look at the left y-axis, which I'm not squaring here, is if you look at those red points on precisely lying on the y-axis, then you see that those cases, they give you an arrow bound that's 0 degrees. That's something that's not make sense. That doesn't make sense, right? And I conjecture those are the cases where the purse is empty. So when the purse is empty, basically there's no single point in that purse. So basically, I'm not, I cannot give you any arrow bound because, the optimization problem is not even feasible. So that's the cases where, you know that your purse is actually empty. So that's, the 90% confident case. Now, if you look at the 60% confident case, you see that things get much better here. But of course, you get much more red points because the red points are the cases where your purse does not contain your ground truth pose, right? So in those cases, you'll get cases where your bounds are not valid. But again, in these cases, if you allow the failure rate to a little bit higher, which means that corresponding to the images I've shown you before, the circles or the ellipsoids become much tighter. But then the tighter prediction sets give you tighter bounds on the ground truth pose. And you see here these things, although they still never cross the boundary of y equal to x, but they get very close to that line, right? So these I think are the best results that one should expect, is to see that these bounds getting very close. The arrow bound is very close to the real arrow, and that's a tight bound that we want. And of course, you still have those things on the right side. Those are very loose. But then, those are the bounds that we've computed, and I think that's the first time that we are able to compute those type of bounds. And sometimes it's actually even tight. So if you look at the now, we want to do some canonical benchmark. We want to kind of we want to compare our average pose with the previous state of the art, right? So we want to see if our average pose is actually better than previous pose estimations. Do notice that here we are just doing this, kind of in the favor of the computer vision community, because or in the favor of the reviewers, because we want because I think the reviewers still want to see if the average pose is actually accurate. But do notice that we are the goal of this paper or this project is to actually give you the arrow bounds. So actually we should be done already by those plots. But here I'm just showing this for kind of ablation study. So here if you look at our average pose, you see that our average pose is actually better than the previous state of the art. So here are the numbers. So the average numbers is a recall. So the recall means the percentage of images where your estimated rotation translation is actually close to the ground truth. So you see that these numbers are actually significantly higher than the previous state of the art. And even if you use FRCNN, these kind of bounding box detectors, they are still slightly higher than the previous state of the art. So basically, by doing things in a more principled way, as a product, we are also getting an average pose estimation that actually is improving upon the previous state of the art. So that's what all I want to say in today's talk. So the conclusion here is that basically we introduce these two fundamental changes into this object pose estimation pipeline, where the front end we kind of conformalize it, and the back end now we're just propagating the uncertainty using the theory, using the results in control theory. And then there are a bunch of interesting things that I think probably perhaps the audience will have questions. So the first thing is, how do you design a nonconformity function, right? And in fact, the sizes of the prediction sets will actually depend on the nonconformity functions. So in our in the paper, we actually discuss why it is actually pretty difficult to design a nonconformity function that can give you a kind of a tight prediction set. But in the future, we are really interested in learning the nonconformity function, because the nonconformity function, I told you, is an arbitrary function. You can actually learn it. So maybe learning the nonconformity function will significantly improve the sizes of the prediction sets, and therefore improve the error bounds on my state estimation. And the second thing that I think is more interesting is actually to compute the Chebyshev center of the purse. So the thing here, I'm really interested in is this min-max problem, right? So given any average pose, I will be able to give you a bound. So can I find the average pose that give me the minimum bound, right? So here, so this is something that's really interesting, because this is kind of in direct kind of in kind of stark contrast with existing works in computer vision where they have to handcraft a cost function to get some post estimator. Here, I'm just trying to find the best post estimator that gives me the minimum bound. So that's very, from the kind of perspective of getting a post estimation that is close to ground truth, this is the best I can do, right? So this, I can find an average pose in my purse that gives me the minimum bound. So that that gives you sort of this min-max problem, which I think that there are actually interesting ways to solve this problem. So I'm interested in exploring that in the future. And last thing that I think I'm excited about is now that we have this type of purse, I'm interested in of course extending this purse idea to different other computer vision problems. So that will gives us some state estimation errors, right? So in control, in robust control, people always talk about when your state estimation is bounded, then you can design sort of a robust controller. But kind of the sad story was that in many cases, state estimation gives you zero bounds, right? State estimation cannot offer you any error bounds. But now that we have state estimation giving us error bounds, how can we now incorporate this error bounds into the downstream planning and control? I think that's another interesting direction to explore in the future. So that's sorry I took much longer than necessary, but hopefully this is interesting for you. And now I think we can I have time, so a few questions, I'm happy to answer that.
Thank you. Yeah, that was really good. I really enjoyed the talk. I'm gonna open up the floor to any questions, although I do think a lot of people have started to drop off. Does anyone have any questions at the moment? If not, I could probably get started on this. Cool. Okay. Yeah. So my main question was in this like downstream planning, like this geometric uncertainty propagation, right? So you're seeing. So from what I understand, you're able to provide uncertainty bounds on the rotation and translation pose, but where does this? Why do you call it a geometric uncertainty propagation? Like, where's that like propagation happening from inside the like? Yeah, that's my main question. Like, where's that happening?
Oh yeah, I think the word geometric basically corresponds to the geometric shapes of the prediction sets, right? So
you've got a set of possible key points. You've got a set of possible locations for your key points on the 2D image, right? But your key points are fixed points on the 3D CAD model.
Yes. So the 3D key points are fixed, because that's a more realistic setup, because in practice, usually you have the CAD model, right? So if you have the CAD model, then you actually know precisely where the 3D key points are.
Okay.
So that's why there's no uncertainty in the 3D key points. But of course, you can extend it to the cases where you have uncertainty in 3D key points, which will correspond to, I think I think it is possible to extend this work to, for example, point cloud registration, where you have point clouds, and then both 3D key points are kind of noisy, right? So in those cases, I think you can do that in those cases as well. But I think this problem is more difficult than that one, because that one is 3D to 3D. This one is 2D to 3D. I think
you have the rational projection.
Yeah. There's this full camera projection, which makes things more difficult.
Right. Yeah. So I'm really interested in the 3D case, because let's say you're flying around with a quadrotor, then how do you register your point clouds in between frames so that your relative translations or relative pose between these frames?
Yeah. And I think for I do think that it is actually possible to apply this to sort of drone navigation indoor, right? And but I think if you were to apply kind of this, if I think this current work is also possible for drone indoor navigation, because in many of these learning-based localization, they are only looking at the image, right? And then they give you a pose. They can do direct regression of the poses. They have a neural network that is trained in the environment, for example, NERF or something else. You can get some type of pose estimation directly from 2D images, and you can, if you conformalize that entire kind of black box, you will be able to get uncertainty as well in your pose estimators. So that I think will bypass the 3D point clouds or 2D 3D cat models. So I think that's also possible.
Interesting. Okay, so you're saying we can like conformalize the registration problem.
Yeah, you can, so I have this kind of a very overview of conformal prediction. So the conformal prediction is like really you can apply to any machine learning problem, right? So you just have you need to have a training data set, where you have X and Y. So in our case, Y are the 2D key points, right? But you can have X being a pair of point clouds and Y being a 3D rotation and translation, and you can conformalize that. And you can have X being a 2D image, and you can kind of Y being the pose directly, and you can conformalize that as well, right? So you can conformalize almost everything, but of course, the performance of different conformalization may be different, and the main concern is sometimes you'll get error bounds that are super large. I think because 2D key points are easier to learn, therefore the uncertainty in predicting 2D key points are actually much lower than the uncertainty of directly regressing poses. So that's why I think doing things in this two-stage way intuitively should be better than doing this in a fully end-to-end manner, or unless you have a fully end-to-end neural network that can predict these poses really accurately. Then in those cases, I think the conformal prediction may work in those cases, but that's to be explored. So I think that's an interesting direction as well. It's like where do you conformalize, right? So at what level of abstraction of the problem are you trying to conformalize it? I think that's also interesting.
Because the other problem that we've been having with the 3D point clouds is how do you know which point corresponds to which other point, right? It's the matching.
Yeah, so in those cases, if you want to conformalize that, I think one interesting thing, I think I've thought about. I think if you were to conformalize point cloud registration, then you would probably want to conformalize sort of the confidence of each of the match being an inlier or outlier. So in some of these registration works, so what they do is they learn some, they embed these points into some high dimensional features, right? And then they do nearest neighbor search to establish putative correspondences. And then usually they have a kind of an extra layer which is trying to predict whether or not each of these correspondences is an inlier or an outlier. So basically that gives you a weight. So it gives you a sort of a probability of that one being an inlier or an outlier. And you can conformalize that. So basically that will give you kind of a upper bound and lower bound in the probability. But I think that's one way. The other way is you can conformalize perhaps also the radius of the search. So because in kind of this nearest neighbor search, you usually have this radius kind of usually they kind of in the feature space they if the distance between two features is less than some threshold, then they think it's a match. But you may be able to conformalize that using kind of a more advanced version of conformal prediction, which I can point you to references. But I think in general this inductive conformal prediction, I think is very at a nutshell, it's doing something similar to like Gaussian processes, right? Because if you do Gaussian processes, it also gives you some upper and some probabilistic upper bound and lower bound standard deviation apart from the mean prediction function. But then Gaussian processes it's kind of difficult to use because if you have a lot of data, you have to solve that problem, which is not trivial. But then this inductive conformal prediction, literally comes for free. You just have to design a non-conformally function, and then you're good to go. But the downside is, I think there's still the downside also is the same for Gaussian processes. How large do you want that standard deviation to be? If the standard deviation becomes too large, then you cannot make any. It won't be useful for any downstream tasks, right?
Yeah, that's really interesting. Yeah, very cool. Nice. Any other questions from anyone else around here? If not, I think we can stop here. And yeah, thank you so much. I'll be in touch with other questions that I might have going forward. Yeah.
So I can also I can also share with you the the paper, it's in my drive. I can share it with you. If you're interested. Just it's not on archive because it's written in media, so it has to go through some IP first before we kind of publish it. But I think it's okay to share it privately. But I want to share because the newer, if you look at the newest version, there it is actually doing things on the single key point, so you lose some of the guarantee. But if you design things in a more clever way, you can actually mitigate that issue.
I'd love to take a look. Yeah, please do send it over. I'd love to take a look.
Okay. Thank you very much, Steph. And
thank you so much.
yeah, hope to see you around.
Hope to see you around. Yeah.
Okay.
Bye-bye.
Bye.